Hello mathematicians, puzzlers, and other curious people. This video goes with a blog post series, so if you've just found it on YouTube, that's fine, but check in the video description because you're missing a little bit of context and seeing what happens next. So in this video, we're using some spreadsheet methods to investigate the behavior of a formula. So I'm using Google Sheets here, but you can use whatever spreadsheet program you want. And we're going to try out some different values of n in the formula n to the power 4. That little up arrow symbol, the caret by the way, you get that by doing Shift 6 on most keyboards. And we're going to take n to the 4 and add to that 4 to the power n. Okay, now our n values, we're going to try out 0 and 1 and a few other things, which we'll be using autofill to make go more quickly. Now, what about actually plugging this in? Now, we could individually calculate each one, and the spreadsheet would still be somewhat useful for organizing it for us, but we can also make the spreadsheet do our arithmetic for us very easily. So we can hit equals to tell the spreadsheet that we want it to do a calculation for us, and then click on our n value, and then put in to the power 4. Okay, what's going on there? Bit of a typo. There, to the power 4. Okay, and then to that we want to add 4 to the power n. Again, going back where we started. And I see it's being helpful with that autofill, so let's go ahead and let it. And we can check that with each one, it's referring to the correct n value next to it. So we can drag that on through. Whoops, what happened? Oh, I see what happened. So sometimes if you just pick one, it will continue incrementing, sometimes it doesn't, but that's easy enough to fix in this case. We just need to choose 2 lines here and then drag that on down. And we can see that these values are increasing very rapidly. Whoa, so much so that it goes into exponential notation. So from here, we're not going to be able to check because just like I mentioned in the other post, we need to know the last digit of the number for a lot of our strategies that we would use to tell if a number is prime or composite to work. For example, we can't even tell without the last digit if it's odd or even, and it's got to be odd to be composite, other than 2, which this is definitely not 2. Okay, so we see that if we plug in 0, we get 1, which is neither prime nor composite. 5 we already know is prime. 32 we know is composite because it ends in a 2. And we see that a lot of these end in a 2. So that, or a 6, same thing, even ending composite number. And is that's centered differently. Is that spilling over? It is. Okay. Even ending composite number. Okay, so I see a few more, and I notice that we have several numbers that end in a 5. So again, those have to be multiples of 5. So those are composite. This number ending in a 9 here, I'm not sure about yet. We'll get back to that. We've got some more that end in a 5. So it looks like we found quite a lot of composite numbers, and 2 that we're not sure of. So let's do a little further analysis on the value we got by plugging in the 5, 1,649. So I'm going to try some different numbers to see if we can get a factor pair for 1,649. So we know 1 would, but that's not helpful because that would just be itself in 1. We know 2 doesn't work. Let's try 3. So I'm going to just use division to help us out with this. Okay, so I see that... Oh, wait, other way around. Always get your division set up in the right order. Okay, so that's not an integer, so that's not a factor pair. Let's see, we know 5 doesn't work because it doesn't end in an appropriate number for it. We can try 7. Okay, 7 works. So we have here a composite number. Okay, so let's basically repeat that process using the value we got from 15 now. So let's see, we have 1,073,792,449. And we just need to try things again. So if we try 3, so we're going to see what happens if we take that number and divide by 3. Okay, decimal doesn't work. Again, we already know 5 won't work because that was a very easy divisibility check to apply. We can try 7, and that didn't work. Let's see, next prime number would be 11. We don't need to try any of the composite numbers as a potential member of a factor pair because we know that they are not factors of this number because the prime numbers below them were not factors of this number. 11 doesn't work, so we try 13. 13 doesn't work, 15, 17, and 19 would be our next options. Let's see, 19, 23, 25, 27, 29, 31, whoops, typo. Always check your work. Let's see, so still we're getting a bunch of decimals. Let's see, 33 is a multiple of 3, not 35, 37, 39, 41, 43, 47, let's see, not 49, that's a multiple of 7, 51 is 17 times 3, 53 we can try. 57 is a multiple of 3, 59. So one thing you might be wondering is how long do we need to keep going? So clearly there's still plenty of room between 59 and 18,199,872 for there to be some more integer factors in there. As we keep reducing this, one thing that will happen is, well, as we increase one factor, the other will decrease. So if we ever see that our factor over here is becoming greater than our other factor, we'll be able to say, okay, wait, we know there's nothing, no place left to hide. Okay, now, even though this is going to make the computer do a bit of extra work, I'm noticing that it's getting a little tricky to make sure that we're checking every prime number here. So I'm just going to pick these last two. I know that any further prime numbers here would have to be odd. And I'm just going to keep dragging that on down and looking for a pair of integers. And this is trying out some things that had no chance ever of working, but it's also trying out every odd number, so that will automatically try out every prime number. So we keep going, keep going. Just looking carefully for some number that might turn out not to be a decimal. So just how long would we have to go on anyway? So one way we can find that out is to consider what kinds of numbers make a factor pair for a particular number. So either you could have two copies in the factor pair of the square root of the number you're looking for, or you could have one that's more and one that's less than that square root. So we can stop looking for factor pairs as soon as we find the square root of the number we're looking for, as soon as we get that high. So let's find out what that would be. So I'm going to take the square root of this number right here. Okay, so that square root would be more than 32,000. I am not doing 32,000 lines of this. That's unreasonable. We might be able to set up some kind of array script to autofill that many lines automatically. I mean, technically it would be about 16,000 because we're doing just the odds, but you know what? Even that would be a lot. We'd still have to check them. Checking 15,000 lines to make sure that there are no nice, neat integer pairs in there? No, we'd be here all day. That's unreasonable. So, to be lazy like a mathematician, what we can also do is find a formula that checks these values for us. So, I did a little bit of Googling, and I found this formula right here. So it's based on an array formula, which means it's going to take advantage of some of the row features and column features of the spreadsheet. And this formula will do pretty much the same thing we've been doing. It'll try values to see if by dividing our target number by that number to see if what we come up with is an integer. And it's going to use what's called modular arithmetic for that, which is basically just based on remainders. So if it is a multiple of it, this thing will be able to tell. So this formula is saying that this value is composite. Now we'd like to double check and make sure that this formula works right. So we can auto drag it up to some others and see that it is correctly checking the right number. Well, is it just saying everything's composite? Let's keep dragging up. And it does correctly detect that 5 is prime. So I think this formula works. So from this, we have a good reason to believe that we have a composite number here. And in fact, it looks like all these numbers happen to be composite. Except up through there, it looks like the formula loses the ability to keep processing. That happens sometimes, but we already know those are composite. Let's see. Okay, so from this, it looks like when n is greater than or equal to 2, that n to the fourth plus 4 to the power n comes out to be composite. Now, this isn't a proof, because we weren't able to check all these, and this formula only works so far. So we don't have an absolute proof of what's going to happen for large values like when n equals 100 yet. But we have some good evidence that points us in a direction that then we can try to come up with a proof for. So let's see what happens next.